It's my pleasure now to introduce our final keynote speaker of FAME 2023, and that's Sanmi Koyejo, who's an assistant professor in the Department of Computer Science at Stanford University. His research interests are in developing the principles and practice of trustworthy machine learning, focusing on applications in neuroscience and healthcare. He's part of the BRAIN team at Google. He serves on the NeurIPS Foundation board and is president of the Black in AI organization. So we're very honored and happy to have him here today, especially because I know it's very early in the morning where he's speaking from in California. So I hope you've got a strong coffee next to you, Sanmi, and I'll let you give your talk now on algorithmic fairness in imaging. Where are we now? Where are we going?
Thank you, Andrew. And thanks for the kind introduction. I'm caffeinating this morning, but hopefully we're coherent enough, maybe more coherent than normal. So what I thought I would do today is do a sort of very short version of a tutorial that I gave in 2022 with Olga on algorithmic fairness, because I think it's relevant and maybe interesting for this community. And I like it because it probes on some of the questions that the community broadly are asking about fairness, and tries to take multiple views on each of these issues. And I hope at the very least it's somewhat provocative and maybe interesting. And maybe at best, you learn something useful that's meaningful for your work. So maybe to set up some of this, I'll quickly set some of this up by some of my own work that's looked at algorithmic fairness problems. I think for this group, this intro is maybe less relevant. I think, a bit of selection. If you're in this meeting and you've stuck around for some amount of time, you probably are interested in fairness generally. But anyways, so we did some work with some colleagues looking at predicting comorbidities of COVID. This was a couple of years ago, and we were very interested in thinking about these topics. And I'm showing this work because one of the things that we found was a systematic difference between the predictor behavior and sort of the error behavior across different demographic groups. And when we did some digging into what was going on, we found out that some of the best explanation for that difference seemed to be tied to language, which is something that I think is sort of not something we think about as often in healthcare work and sort of impact of algorithm people. But our best explanation was that the ability of people to communicate with their caregivers had a big impact on how the care was actually given, what kinds of tests were done, and the actual outcomes that these people had. And it showed up sufficiently strongly that this was a very sort of non-trivial systematic effect across the different groups. So again, for this audience, we have now lots of examples of these kinds of issues, of various concerns about differences in algorithmic systems across individuals or groups, which we think of as fairness and bias in medical imaging. And we care about these problems. I imagine someone has brought this up, but maybe as the end of the day, I can remind you about some of the reasons we care about these questions. So they include the fact that unfair algorithms lead to unfair allocation of opportunities or resources or information, and all these can have meaningful effects. They can lead to different quality of service once algorithmic systems are scaled up across people. They can reinforce societal stereotypes of various kinds. They can denigrate people or be offensive and over and underrepresent people. And all these things are especially worrying in healthcare type environments where we're worried about impacts on people's health. And so today I'll talk about three of the narratives that I think may be interesting in the algorithmic fairness work and how it ties to, again, give multiple sides of this sort of view on existing and upcoming work in algorithmic fairness. I should mention that in the tutorial, which was 3 hours, we did 7. So this is sort of much, much shorter, condensed, and some things are updated as well over time. So I think there's a impression that parts of the fairness issue can be solved by picking the right features. And I think this is most strongly taken by folks outside of the technical community, at least as far as I have seen. There's this idea that if I don't use demographic features in whatever system I'm building, then I should be blind to demographics, and I should not have to deal with algorithmic fairness problems. And often this shows up within the life cycle and how we think about building algorithms. So this sort of idea of feature selection, and I'll touch a little bit on representation learning as a version of this question. So as I was saying, there's this idea of fairness through unawareness. I think for most folks who work in this field, it's very clear that this cannot work. And generally it doesn't work because features are strongly correlated with each other. So if you're looking at demographics, those demographics are probably correlated with language, correlated with location, correlated with a bunch of other features, such that simply removing demographics is not enough to actually get an algorithm that will treat different groups the same way. But if you're technical, I think you then get enamored by maybe the technical solution. So this question of, well, maybe we can just throw some machine learning on this. Can we learn a version of the data set that doesn't have any societal biases? And this will remove this issue, this sort of whatever's causing our fairness problems. And so broadly within the field, as many of you know, this idea of learning better or learning different features is called representation learning. So I take the inputs, my data, and I try to learn some other features that are informative for whatever task I'm interested in ideally. But in this setting, we're most interested in the idea that they remove potential bias sources in a data set. And I think this kind of question, I think very strongly was called on in some of the work Judy did recently, where they looked at a bunch of medical images. And what they did was just a bunch of many steps of degradation of these images. So they looked at filtering the images in various ways. They looked at many other things that you can do to the images such that for a human, you can't tell. So it's probably worth saying, you know, on its face, outside of some very strong biological features for some kinds of x-rays, generally you can't tell many demographics from biological images. I think strongly, I'd argue it's quite hard for a human to tell race from biological images. Nevertheless, they found that for the images themselves, they could do this quite well. And then even if you remove lots of human interpretable information, you can still build algorithms that can predict race quite well. And the inference from this is that, again, there's enough signal left over such that you can catch what you would have imagined should not be easy to catch. Again, this sort of idea of being able to capture race from medical images. And on one side, I think this can be challenging when we use these kinds of, so one approach to this is try to sort of, as I said, explicitly remove protected attributes from the prediction. So here I'm showing an example from a CVPR paper from colleagues, Wang et al., that looked at building a representation system, looking at how much the representation seemed to cluster across demographics. And then looking at methods that could remove this strong correlation. And so what they learned is a new feature space or new representation where there was sort of much less signal about demographics and representation. So this is in some ways what we might want when we're looking to debias representations. However, what they found is that in the original representation, the sort of signals they were interested in were also sort of highly clustered and so quite well predicted. However, once they looked at the prediction task after creating fair, so this sort of demographically uncorrelated representations, the labels were much more mixed. And so this is a setting where there seems to be a real tension between the ability to remove demographic features from the data we're building and the ability to sort of learn predictors at a high quality. So this accuracy fairness trade-off that we sometimes get shown. So I think overall, representation learning is an interesting approach, sometimes meaningful, for mitigating some of the, at least naive ways that bias can come into our predictive systems. I think, though, on the other hand, it seems quite hard to fully remove them. I think the reading race example is salient on this. There are other examples in the longer version to point to where that do seem to be sort of non-trivial, meaningful differences among demographics in imaging or whatever measurements that we have. And I think there are reasonable questions about to what extent, what we should do given that these correlations often exist. So are they harmful by themselves, or are they harmful because of downstream impact? And if it's the downstream impact, perhaps we can build systems that accommodate for the fact that there are going to be differences across demographic groups in the data that we're measuring. It's also worth, I guess, adding, sometimes we get a bit overconfident when we build algorithms. So thinking of sort of fairness being solved, quote unquote, with feature transformations, I think can lead to carelessness. Again, often there's attention. Again, often signals persist. Okay, I'll switch to the second narrative. So the second narrative asks this question of metric definitions. So this idea of if you can measure it, we can build some learning problem. You can essentially come up with some kind of loss that captures whatever it is we're measuring. And once we have that, we can build some learning system that sort of minimizes that loss, and that will solve our problem. So in our cartoon box here, again, I think about this as the sort of outcome definition kind of work. And I'm highlighting this partially because this is a question I've been quite interested in. So we've done some work that I just mentioned briefly on this question of how do we determine metrics or measures that best reflect stakeholder preferences. And so our approach to this has been what we called metric elicitation. You can think about this as sort of active learning for loss functions. And so the idea is, can we interact with stakeholders in a way that is sensitive to sort of the cost of question answering, so this preference learning. So we want to be as query efficient as possible, yet still get a good proxy for what measure, either performance or fairness or other things, that best matches the preferences of stakeholders. So we've done this work for individuals. We've done this for some early thinking on how to do this for groups of stakeholders. We've also done versions of this for fairness types of applications. On this narrative, I think one side of this is within the field, there is a lot of the algorithmic view, I think, likes a lot the formalization the metrics bring. So, once you have a well-defined measure, I think it feels straightforward to try to build algorithmic systems that can, again, optimize that measure. So that's something that people seem to like. And as I've mentioned, some of our work tries to tackle this by elicitation. So let the stakeholders tell you efficiently what they would like to measure and optimize. I think the other side of this, though, to keep in mind is that we're depending quite strongly on the judgment of stakeholders. And there are lots of challenges in how humans perceive the task and what exactly they end up sort of telling us in terms of what the preferences are. And we've seen examples of this in some of our work on human biases making this problem somewhat more challenging in certain cases. I think also it's just worth saying that metrics are not universal and can be hard to select. I didn't have a chance to give this example because of time, but I'll mention, changing the setting that you're in, so changing the context, can change what the right metric is. So, taking some metric that we think of as, say, good for performance or fairness, going from, say, a high resource setting to a low resource setting, can change the problem quite significantly. And the right way to handle this generally is that we should be reevaluating what we're measuring as we deploy systems. And this can be expensive and tricky to do and sort of do correctly. And so there is this tension of the push to algorithmicize systems, and because we think this can make them more efficient, but then the challenge of doing this in a good way such that we can correctly capture local stakeholder preferences. along those lines, it's worth mentioning that, ideally, this is not something we do once. Ideally, the way that you measure whatever your algorithm is doing is done over time as you deploy your system. And you should improve these metrics, allow for unexpected failures. Ideally, do this after you've deployed your system. And so, again, this makes the challenge of figuring out what the right measures are potentially quite complicated. Okay, I'll switch now to the third narrative. So the third narrative asks about data, because I think, again, the very obvious way we think about many of the fairness issues boil down to something wrong about the data we've measured. Now, I'd like to, again, consider this issue from multiple perspectives. So, the data part, I think for anyone who's built real systems, will appreciate that data is extremely important, and I think often underappreciated when we're thinking about algorithms and deploying systems, because again, so much of the effect of machine learning and AI systems ties to the data we've collected and data we've deployed. And so while most of the focus is on the data, I want to talk a bit about some work on post-deployments that shows that there can still be issues despite the fact that you've maybe been careful about data collection tied to potential fairness concerns. And maybe a cartoon to set this up. So, this is hopefully not how we think about machine learning systems anymore, but there's a long time where we thought about machine learning systems as sort of pour data, do a bunch of linear algebra, collect the data, and collect the results on the other side, and just sort of massage the whole thing till the results start looking right. I think now, hopefully, we have slightly more systematic view of what these problems are, or what it is to build and deploy a good machine learning system. Nevertheless, I think in practice, things often look like not too far from this cartoon. So one of the issues that can come up is distribution shifts. And I suspect some of this might have come up earlier in the workshop, but this question of, if I build some algorithmic system and suppose I'm actually able to get the properties that I want. So here we're looking at building a system and having some fairness kind of measure as part of the system building, and asking what happens at deployment. And this paper is interesting. This is a paper with Shroff and a bunch of other colleagues. One thing that's interesting about this paper is that most of the distribution shift work has focused on performance. So, it's sort of well known, I think now, that if you build a machine learning system, the performance of the system is not guaranteed once it's deployed. I think it's been less appreciated that it's not just performance that can change from training to deployment, but sort of lots of other properties that you thought you baked into your system can change from training to deployment. And this paper specifically asks the question of fairness properties. So, you train your system, and the top of these, so the top line around 85 to 90, we have subgroup performance. The idea is we're measuring fairness by differences in performance across different subgroups. And what you can see is that in the source setting, in this dermatology problem, this is from dermatology images to labels of skin conditions. We have sort of very low differences across demographic groups. So this is both male, female, and also age groups. And so, from many ways of looking at what it means to build a good system, we've built a good system. Like it actually has good performance and then similar performance across groups. Yet once you deploy the algorithm, what we find is that all of a sudden, the differences that we thought were small at deployment can be quite big. Again, it's one of those things where once you show it, I think for many of you will not be surprising, but I think is also a question that hadn't been considered carefully and can be surprising if you are not expecting it. And so I think the challenge this brings to building systems is, again, thinking not just about systems in isolation and training, but what happens after deployment and what happens to properties that we like fairness properties, once we build and deploy the system. So what is the effect of distribution shifts? And in this paper, we do a little bit of a deep dive into some of the causes of the distribution shift and potential initial solutions. But I think there's a lot of work that can be done to try to address these issues. Another view of the fairness problem that I think can be interesting is, and this I think came up briefly in the last talk, but I'll touch on this in a second, is this idea of adversarial vulnerability of algorithmic fairness. And so this is interesting. Again, one of those issues that are well studied in standard performance settings, and I think much less studied when we're thinking about other properties of algorithmic systems beyond performance. So this paper looked at sort of measuring algorithmic bias and then asking questions about to what extent you can construct adversarial attacks such that at deployment, your system has sort of much worse fairness properties than at training. And I think this is interesting on its own, just to understand the properties of systems. So this tells us, something about maybe the worst case behavior that we can have when there are shifts between training and deployment of systems. I do think there are possibilities of adversaries, and I'll touch on this in sort of this issue of intersectionality, where it's easy also to imagine either well-meaning actors or explicit adversarial actors building systems that have some of these issues. So we did some of this motivated by some work by Kearns et al. So what they did was define this term fairness gerrymandering, which I think is kind of interesting. You may have seen this before. The idea is that you can build algorithmic systems to be sort of fair as we would like when measured across pairs of demographic groups. So in this example, I'm looking at, say, a predictive system that has good behavior in terms of differences between old and young, black and white, and male and female measured separately. So in each of these things, the algorithm behaves well. However, if I look at subgroups, so if I look at, say, black female, or maybe white male versus black female, I can have quite big differences across those subgroups, even though the overall average groups look fine. So just, again, to be explicit, in the algorithm, there's a small difference between average over, say, black and white patients. There's a small difference on average between male and female patients, yet the algorithm has found a way to have white male patients have a very, very different performance from black female patients, even though the averages look okay. So this is a question of sort of issues in the algorithm that can come up if there's an adversary or sort of a mistake in the system or a bunch of other issues where averages look okay, yet different subgroups can suffer very different kinds of harms. And sometimes this is used as an argument for looking at individual fairness versus group fairness, but I'll maybe highlight that the adversarial vulnerability issue is an issue for all algorithmic systems and not special to group versus individual. Really, it's sort of any system you build, there's always a potential for adversarial vulnerability, as you might already know. And so this is an ongoing issue that the field should be thinking about more. So as I said, some of this is due to hiding outliers. So averaging has this effect of removing some of the extremes. We found that this doesn't seem to happen in our experiments in sort of standard learning systems with limited capacity. So I don't know, linear models, some regularized deep learning models. However, I think it is possible that sort of if you have a very flexible model or an explicit adversarial builder, or just a company that wants to build a system that passes the fairness check while not actually serving all these as well. This is a sort of known issue that can happen very easily in algorithmic fairness systems. And I think one argument as a counter is to maybe avoid averaging as the main mode. If we know something about the groups that we'd like the models to behave well across, we want to maybe build our measurement system such that we're not doing explicit averaging and have other mechanisms for measuring explicit subgroup differences and optimizing against that. And so we have some work a couple years ago that tries to look at this problem and give efficient systems for solving these issues. I think another issue that can come up in machine learning deployed systems is delayed impact. So this is the question of sort of building systems thought of in a static way. So we build our most machine learning systems, think of as sort of, we build a system, it gets deployed, we just look at sort of one-off outcomes of the systems. But in many cases, machine learning systems, once deployed in the world, have a feedback loop kind of effect. So it gets deployed, the deployment affects the behavior of people. Behavior of people changes either the prediction we're going to make in the next cycle or over time, or the data that we measure. And this paper and other papers have looked at this question of delayed impact and actually show cases where well-meaning algorithms that are tied to, say, improving fairness in a one-shot way. So I'm going to build a system that's going to have good fair performance in my measurements, instead of in a training test kind of way, can actually lead to harm in deployment because it changes the behavior of the overall system. So it changes how users behave, patients behave, practitioners behave in such a way that there's actual harm at the end. So somehow we have an unintended consequence of building algorithmic systems. So on one hand, I think training data is a big culprit often when we have issues with our algorithmic systems. However, it's not the only one. There's lots of other aspects that we should be thinking of when we build systems. So feedback loops, distribution shifts, delayed impact, and we should be sensitive to all of these and try to build our system to be robust to as much of these as we can. And again, I think these can come up in any step of the pipeline. And importantly, fairness properties don't seem to compose in general, meaning if I build a system that has multiple steps, if I have good fairness properties at, say, step one, my data selection, for instance, it doesn't mean that subsequent steps will retain these fairness properties. So, you know, sometimes we look only at training, but I think there are lots of other issues that we should be looking at. Okay, to wrap up, so fairness, I haven't done full justice to this, but you've, I think, heard about this over the course of the meeting. Fairness is socio-technical. Algorithms can be meaningful and help us think through what the avenues and the mechanisms we can build are to improve our systems, but it can be incomplete and really needs to be thinking end-to-end with stakeholders in mind and how we think about fairness issues. And we should especially try to avoid oversimplifying. So respect the fact that these are challenging problems that need sort of holistic systems views to really solve problems in the real world. And maybe accept that sometimes for these kinds of issues, the solutions might have to be complicated and ongoing, that we need to be building systems that are adaptive to how the world is changing, and maybe put more research resources in these directions. I didn't get to talk about this, but I'll just mention that I think it's also important to think about who builds the systems, because this affects what data is collected, what kinds of questions are asked, how we choose to evaluate. And so it matters often that we have representation in the builders, because I think this affects the downstream impacts of the systems that we build. And then I think this is a tricky and sensitive one, but worth saying. And again, for this group, I'm a bit preaching to the choir here, but while these questions are hard, often everyone likes to punt to someone else in the chain. But I think meaningfully, folks who are building tools should be engaging these questions. And part of the reason is that we often have the best technical view on the problem, and that's important for thinking through end-to-end what solutions might look like. And so I'd like to encourage, again, many of you are already doing this, not punting away fairness issues to say some other part of the chain will take care of it. It really does matter that we're thinking about these questions. Okay, with that, I'll end. I talked about a couple of narratives and many more in the tutorial if you're interested, and I'm happy to follow up if anyone wants to follow up on any of the threads that I talked about today. Thank you for having me.
Thank you so much for your talk, Sanmi. We have maybe time for a couple of questions, but then also, of course, we have the panel discussion afterwards where we can go into more of these points. And I think what actually you shared in the end would be also great to talk about in the panel, maybe if Ben can do that. But for now, we have one question from one of the panelists. Do you think in medical imaging applications, it's desirable to completely remove protected group-related information from the representation? and whether that's even possible, and how that maybe relates to like how clinicians routinely make use of such information for diagnostic tasks?
Yeah, so I think in general, I think the answer is no. I think, again, this is the unawareness argument. So like if I remove it, this fixes the problem. I think there's so much else that ends up correlated that well-meaning removal of demographics often just leaves enough signal there that, if in one extreme, if they're bad actors that want to say be using demographics, they just use other proxies and have the same effect. And even well-meaning or even algorithmic systems on the other extreme can sort of very easily inadvertently end up extenuating these issues if you simply just remove demographics. So I don't think it actually fixes the problem, just meaningfully to state this. I think, recognizing and then building the rest of our ecosystem around the fact that these issues exist, I think is meaningful. There's some challenges in healthcare specifically because we don't always know which of the signals are sort of demographics due to, say, historical or data issues. So differences due to those issues or differences that are actually biological. And I think this problem is meaningfully more challenging than in many other cases where, the culprit is much more clear. Nevertheless, I think observing sort of demographics and sort of being aware that this can color the way that we build systems, I'd encourage as sort of the best way to try to handle some of these issues.
Thank you so much. I think in the interest of time, we can go over to the panel. So I'll hand over. Thanks again so much for your talk. And then, of course, you will join us. I'll hand over to Ben, who will be chairing the panel discussion.